Welcome back, folks. Playing with phasors. Pew, pew, pew. Everything we do with DC analysis, everything we did up until the point where I said the word phasors, we can redo again for AC signals, sinusoids, with phasor analysis. Okay? That includes Thevenin's theorem. So here we go with Thevenin's theorem. So there's a circuit, and we're going to find the Thevenin equivalent of it between nodes A and B. So we do the same stuff. It's kind of the moral of this whole section is we do the same stuff. Okay, so let's go find V open circuit. I'm going to copy this. I'm going to save that for later. Okay, let's go find V open circuit. So we find V open circuit here. Let me do a different color, just so it sticks out from the original problem. V open circuit. Okay, there's one mesh. So we can go ahead and do one mesh. We can call that I, and we're going to write a KVL since there's no current supply. Okay, so our KVL over here for I, we're going to go up 5 at an angle of 30 degrees. We're going to go down J20. My habit is to always put the impedance in parentheses just so I don't screw up signs, right? I'm going down. The impedance inside there is J20 times I, and I'm going to go down. Here's a good example. I'm going to go down negative J10 I1. That's just one of those habits that I've gotten into to keep me from screwing up signs. Okay, we're back to where we started, so that's equal to 0. Okay, 5 at an angle of 30 degrees. And I'm going to bring these two over, so it's going to be positive J20 and negative J20. So that's going to be J10 times I. And then we can solve for I. I is equal to 5 at an angle of 30 degrees. That was a voltage, right? That's that voltage. And we're going to divide by J10, which is an impedance, J10. Okay. Ooh, I can do this one in my head. Study your complex numbers, folks. Let's see. This is going to be 500 at an angle of negative 60 degrees, and that's in milliamps. Okay, and just because I don't trust myself, I'm going to throw it in a calculator as I knock stuff over on my desk. That's the best thing about the green screen is you can't tell how absolutely trashed this place is. It's like I'm in my office at work, right? On campus. I've been churning out these videos as fast as I humanly can. It's also why you see little imperfections. Like I didn't fight my font in my notes to push those in the right place. I do apologize. I did it right in my head. I should trust myself. I won't trust myself. Okay, that's not I1, that's I. All right, and then if we want to find V open circuit, we've got to write a KVL, and we know that there's no current flowing here. So this one's 0 volts. So the one that we're really after is this one. What's that voltage? And we're going to find that VC. We're going to find that by taking I and multiplying it by negative J10. Okay, so let's see, we take I and we multiply it by negative J10. So it's going to be 5 volts at an angle of negative 150 degrees. And that's going to be in volts. Again, I don't trust myself. So we're going to multiply that by 0, negative J10. I should have trusted myself. I was right. Good for me. Okay, so writing that, we can see that it's VC minus 0 minus V open circuit equals 0. So V open circuit is simply equal to the voltage across that capacitor. Okay, so V open circuit is V Thevenin, and that is 5 at an angle of negative 150 degrees and volts. Okay, halfway there. That's our first result, kind of intermediate result there. The next thing we need to do is find the Thevenin resistance, but it's not a Thevenin resistance anymore. Guess what it is? It's an impedance. Okay, so we're going to find the Thevenin impedance, and that impedance is going to be in series with the Thevenin voltage supply that we just found. So we play the same games. We're looking for Z Thevenin, since it's an impedance. Looking back into the circuit this way, we can use any of the three methods I taught you in previous videos. Method 1 seems to be just fine for this one, okay? So we can see that hopefully you can see that the inductor and the capacitor are now in parallel since I shorted the voltage supply. And that's all in series with the resistance. So we can say that Z Thevenin is equal to R in series with Z sub L in parallel with Z sub C. Okay, since there's only two, we can do the product over something, which is good times, right? So we get 10 plus J20. I'm going to throw some parentheses around here. Again, another habit. If I have a complex number, my habit is to throw parentheses around it, especially in rectangular, because you get into problems with distribution. And we have J20 plus a negative J10. Okay, so we just got to do that quick, and then don't forget to add 10 to it. So we have 0 plus J20 times, I could do this one in my head too, 0 negative J10 divided by 0 J10, all of that. So that's 20 at an angle of negative 90, and all of that added to 10, and that's where things get ugly, because we have 22.36 at an angle of negative 63.4 degrees. Let me just scroll over. Yep. No like crazy exponents on the angle. So it's an impedance. That one's in polar form. There's nothing wrong with depicting the impedance in polar form. We tend to do it in rectangular because we find individual components in rectangular form. But as long as it's locating the same point on a two-dimensional plane, it's an equivalent number. Okay, so there's our second intermediate result that we needed. And then we just have to put them back together, right? So we draw them. It's going to be a voltage supply that looks like that. Where's V Thevenin? Okay, so I'm going to come grab this. 5 at an angle of negative 150. I didn't leave myself enough room. I made some decisions, and now I have to live with it. It's the nature of engineering. Okay, that's V Thevenin. Okay, I got to draw a circle again. I think I'll live. And Z Thevenin, that's a huge, that might have been overkill, is an impedance in series with it. There's node A, there's node B, and get out of there. Come on. There we go. Say it with me. I love technology. I love technology. That's what I teach, but I could use a break from it now and again. Okay, so there, that's in ohms. I should have had ohms up there. That's your Thevenin equivalent. If I take a load and I put it between A and B on this equivalent circuit, or if I take that same load and I put it between A and B on the original circuit, it's going to see the same phasor voltage, it's going to see the same phasor current, and it's going to see the same power. Power is a little more interesting than just phasors. Okay, we can do all of that stuff. If you can do Thevenin, you can do Norton. I'm not going to do a specific Norton example. I think you're I hope you're getting the point by now. What I will do, however, since I can do Thevenin and I can do Norton, that means I can use source conversions. So I'm going to do a source conversion problem for you, and then that's going to be the end of our phasor analysis for this class. Then we get to move on to new stuff. Cool. Okay, Stay tuned and good luck.